Hi, welcome to today's class. Today we're going to be talking about the vector equation of a line. We can now talk about vector equations of lines in two dimensions. And at first you may think that this is incredibly hard, but actually it's the easiest of all the vector problems. Let's start with the definitions. The vector equation of line L. Here is line L. This black line is line L. The vector equation of line L in the direction of vector B. Well, we've also got a vector B that's going down this way. So think of it this way. This is line L, but vector B is on line L. Vector B passes through point A that is a position vector. Well, we know by definition position vector means our tail is at 0, 0. R is equal to A plus lambda B. Well, what does that mean? We're going to try to find out the equation for line L, and we're going to see is we can get to y equals mx plus b or ax plus by equals c, standard form of line L. That's from Algebra 1. By thinking about the three vectors, R, there's one vector, it's a position vector because its tail is at 0, 0. A, which is a position vector because its tail is at 0, 0. And this vector B, which happens to be in the same direction as this line L. Well, it turns out that R, this vector R, is equal to, well, to me it makes sense. If I'm talking about R, I have two components. I go up A and down B. To go from 0 to the end of R, I have to take this path, here and then here, and it gets me to R. And we know that by the first things we did in our introduction to vectors, that this vector can be defined by two other vectors. So to get to the end of R, we go up A and down B. But B may be huge, so we only want a portion of B. Say lambda is 1/4. For example, if we wanted 1/4 of a huge B, well, I'm going to go up to this point A and then down 1/4 of B, or some fraction of B, and it's going to wind me up there. That's the whole concept here, that this vector R can be described by two vectors, this vector up and this vector down. Well, it turns out that this vector down in this direction is not going to be the whole vector. It's going to be some portion of the vector. We don't know that portion, so we're just going to name it the Greek letter lambda. Remember this, R is equal to A plus lambda B. Let's further develop the story of a vector equation of a line in two dimensions. First, you have to buy into this picture that I've got a line L, and I've got a vector R, and a vector A, and a vector lambda B in between them, because B is in the same direction as my line L. You have to also know that point A here is designated by X coordinate, Y coordinate. When I write them horizontal like this with the comma in between them, I'm talking about coordinates on the coordinate plane. This is over X, A1, and up A2. Those are X and Y coordinates. And point P is X and Y coordinates. I'm going to call them X and Y. Well, I can see that this is important. Vector R is simply vector A plus vector lambda B. Well, what is vector R? It's a position vector. Notice that I changed from point P is X comma Y to vector R says go over X, that's my X vector, and then up Y, which is my Y vector. And notice point A, which was coordinates A1, A2 here, says it happens to be that if your coordinates are A1, A2, and it's a position vector, meaning the tail is at 0, 0, then your vector will also be A1, A2, but written like this, because it's saying go over horizontally this much and go up vertically this much. That's the vector. We're defining this vector A in its components, one parallel to the x-axis and one parallel to the y-axis. Plus lambda, well, vector B is given in vector form already. It's saying go over this far, B1, and then go down, B2. That's a vector. That's in vector form. So now we have R equals A lambda B, which you have to remember, and substitute in for R, X, Y, because that's its position vector. Substitute for A, A1, A2, because that's the position vector of this point A, and substitute in your X and your Y for your vector B. Notice, slope is always rise over run, but vectors are X component over Y component, and that can get confusing. Until you memorize that, you're going to have trouble. X component over Y component is our vector. If you've followed me so far, maybe you'll be able to see this too. We know that R equals A plus lambda B. And we can break that up into the position vector of R, which is over X up Y, is equal to the position vector of this point A over A1 up A2 plus lambda, some factor, which I don't know, times over B1 down B1. And that's the directional vector, not the position vector, but the directional vector of vector B. Well, we then can take the jump to the parametric form of equation of a line. Don't forget, we've got this line that we could define as y equals mx plus b from Algebra 1. Now we're going to do it in terms of vectors. Well, this line is really, my x component is x equals a1 plus lambda times b1. There it is. And my y component here is y is equal to a2 plus lambda times b2. And there's that. So x equals a1 x equals a1 plus lambda b1 and y equals a2 plus lambda b2 are my parametric forms of the equation of this black line here. See if you can follow me here. If you've understood that x equals a1 plus lambda b1 and y equals a2 plus lambda b2 are the parametric forms of the equation of a straight line, then let's solve for lambda. Minus a from both sides gives me x minus a1. Divide both sides by b1. We get lambda equals x minus a1 over b. Subtract a2 from both sides and then divide both sides by b2 and we get y minus a2 divided by b2 is equal to lambda. If lambda equals this and lambda equals that, we can substitute for lambda and set these equal to each other. So x minus a1 over b1 is equal to y minus a2 over b2. And this is called the Cartesian form for the equation of a straight line. Yes, do you have to memorize this? No, just think it through. You know how you got here because we started with r is equal to a plus lambda b. R is equal to a plus lambda b led us to split this up, and then that led us to solve for lambda. Solving for lambda will bring us to the Cartesian promised land. We're talking about lines in two dimensions, and it's important to remember that two lines in a plane can either be parallel, so they never, like train tracks, they'll never meet, and they can intersect, so we can get that xy point where they intersect, or they can coincide, one on top of the other, and so that means they intersect at infinite points. Those are our three situations.